This is my report on Lab 4, Circuits and Capacitors by Julian Perez. The purpose of this lab was to predict the way that circuits would behave when containing resistors. This was also followed by how circuits would behave when using capacitors. In this lab, a multimeter was used to measure the voltage drop and the current in the loop, and this was used to make predictions for both DC circuits and RC circuits, and Circuit Constructor Kit was used to simulate this lab. The main physics concepts used during this lab were the loop rule, which states that the voltage across a loop is equal to 0, the current conservation, which states that the current in to a node must be equal to the current out, and Ohm's law, which relates voltage, current, and resistance. The first part of this lab involved identifying the amount of current going through a circuit. This was easily done using Ohm's law and taking the resistance in the circuit and the voltage in the circuit and then solving for the current. As current is a measure of charge per second that goes through the circuit, the changing of the ammeter had no effect in detecting the current. When placing both a voltmeter and an ammeter in series with batteries and resistors, what was found is that the current going through was equal to 0, while the voltage drop was equal to 3 volts. The reason for this is that voltmeters have very high resistance, which results in almost no current coming out of the batteries and resulting in no current going through the circuit. The reason for the negative 3 volts is because the red probe is actually on the negative end of the battery instead of being in the positive direction. The next part of the lab involved measuring the voltage drops across specific parts of the circuit. Across the batteries, there was a voltage increase of 3 volts. Across the ammeter, there was a voltage decrease of 0 volts. Across the resistor 1, there was a voltage drop of 0.959 volts, and across resistor 2, there was a voltage drop of negative 2.042 volts. As this is an ideal simulation, the resistance across the wires at any point was 0 volts. This results in the delta V of the overall circuit being 0, which is correct. By graphing the voltage relative to the circuit, one can see that it rises at the batteries up to 3 volts and then decreases proportionally to the amount of resistance at each segment. So if there's 0 resistance, the slope is 0. If the resistance is greater, there is a greater negative slope. And over the ammeter, the slope is 0 as there is no resistance. The final part of the lab led with a RC circuit that was set up with a capacitor of 200 millifarads and set up with a battery of 9 volts. A light with a resistance of 30 ohms was then placed in series with the capacitor. The following calculations were done by the lab. Because the voltage drop is related exponentially to the time, it is easier to display this as a linear relationship by taking the natural log of both sides. This results in the natural log of the voltage drop across the capacitor over the initial voltage drop is equal to negative T over RC. By taking data, it can linearly be extrapolated that the slope of the line is going to be equal to negative 1 over RC. The voltage drop across the capacitor was measured about 1 time every second. As mentioned before, it is beneficial to take this voltage drop divided by the original voltage drop, which was 9, and take the natural log of that number. By using that as the y and t as x, a linear relationship emerges. Overall, the calculations were very close to the true value, which would have been 6, and it gave 6.05 and so on, which is only about 5% off. The first question asks, how does an ammeter in real life differ from ideal situations? Well, in ideal situations, an ammeter has 0 resistance. However, in real life, it would have some resistance. This would lower the current that would be displayed and would slightly influence the results. The second question asks the difference between hooking up a battery directly to the capacitor with no resistor and the difference between doing it in real life and in an ideal situation. In an ideal situation, it would be charged immediately. However, In real life, it would probably A, set on fire, and B, be slowed down by the resistance of the wire, which, though negligible in most accounts, without a resistance needs to be considered.